In our first numerical example of working with forces as vectors, we're going to take a look at a eye hook that has been attached to a wall, and we got a series of forces that are imposed on it. Now sometimes in these early on examples in statics, the nature of them are sort of confusing because you're not doing the entire problem. You're only working on some subset, because we haven't formally introduced equilibrium yet and those kinds of things. The big picture of what we would be doing oftentimes is we'd be asking, with these three applied forces to this little component, what's the reaction at the base? That's the equilibrium question, which is in the next little submodule. So first we're just going to figure out how to work with these three different forces at their different angular orientation. I'm going to sneak in here what's ultimately equilibrium because it's fairly intuitive and you can easily handle it without having a lot of theory imposed on top of it. Right? But the big goal here is really just to work with different representations of these forces. Right now you'll see that we've been asked directly to determine the magnitude of the resultant force of only two of these forces. F1, that's the 600 Newton force over here at 45 degrees from the positive x-axis, and F2, that's 800 newtons acting at 60 degrees from the positive y-axis, but over here into what would be called quadrant 2 in the Cartesian coordinate space. We're not going to work with F3 right now. Now, there's three different approaches to how we could do this, and one of them is a graphical representation of this resultant. Now yes, we could really work this out truly with the graphical form of putting these into to scale and in their proper angular way of doing that, and what that would begin to look like then is we start here with some point representing this origin point of application of the one force, recognizing that any of these force vectors can be slid along their line of action, and that changes nothing about the overall effect. Right? So then we get out our protractor, we lay out that force to scale, and so maybe that would be here at 45 degrees, and there's your 600 newtons. And this would be a tip-to-tail construction. That would be F1. Then we go to F2, and we put in a new coordinate system here at the tip of our vector. And we would then measure out from the positive y-axis going counterclockwise 60 degrees. And then again, we lay this out, this vector 800, out by scale. That'd be tip-to-tail construction, and the resultant then would be to go from the very beginning, which is way down here, and then take that on up to there. That would be the graphical representation of the addition of two vectors. And if we did this to scale, we could then get out our protractor, measure the angular orientation, measure the length of that r, and we would have our answer. That would be the true to scale way. That's the way it might have been done 60, 70, 80, 100 years ago. Now what we do is somewhat similar in the graphical representation, in that we might go ahead and say, okay, we'll lay this out notionally, but we don't worry about the perfect scale. We'd like to get things to a relatively correct scale because it helps in our understanding, but we'll let the math take care of the rest of this. So we lay that down. There's your 600, your 800. Here's the side that represents the r that we want. So we know two of the sides, but we don't know the third side. We do know some angular references here. We know that the 600 is at 45 degrees from the positive x-axis, and we know that the 800 is at 60 degrees. Which means that we could find out this interior angle. That's obviously 30 there, and that's 45 here. And that, so note now that we have this triangle, and that helps in the calculations when we go back to consider that we know law of sines and law of cosines. Law of sines is helpful when we know two angles and we know one side, then we can find the other one, and we can manipulate those around. So we need to know those two angles to do that. Law of cosine says, well, I only know one angle, but I know 2 of the sides, and then I can find the length of the third side, which sounds an awful lot like what we have here, isn't it? We know one interior angle, we know 2 of the sides, we don't know this opposite one. That looks golden for us to play with log cosines. So let's try that. That we'll have r squared is going to be equal then to our, let's see, we'll call the 600a, so that's 600 squared plus then the other one that we know, 800 squared, minus 2 times 600 times 800 times cosine of the angle that is opposite of our unknown, which is r, and so that angle is cosine of 75 degrees. Let's work it out, see what we get here. 600 squared plus 800 squared minus 2 times 600 times 800 times 75. Cosine, I am in degrees, so that's good, and that equals a big number of 751,533.7 and change. Take the square root of that. That's 866.9 that r would equal. And that would, of course, be units of Newton. Now, we'll handle significant digits here in just a moment. Now we need to go find these interior angles somehow, some way, because we need to find out what the overall orientation of r is. We know that 600 is at 45 degrees from here, but we don't know that one right there. And so we don't know, let's call this top one alpha, we don't know this bottom one beta. It looks like it might be easiest to go find beta, so let's use law of sines to do that. Right, and if we do that, then what do we get? We've got, let's see, we want to find beta, that's opposite of the 800. So sine of beta over the 800 would be equal to, well, now I know that I have the 75 and I know r, I have the 600 and alpha, I don't know that one. So let's use, since we know r, and I still have it in my calculator here, we've got sine of 75 degrees over 866.91, it turns out to be. And so we can solve that then for sine of beta. That would be equal to 800 divided by the 866.91 times the 75 degrees sine, and that's equal to 0.891. Take the inverse of that, and we find out that beta is equal to 63.0 degrees. Okay, so that's helpful there. That tells us not everything we need to know, but it tells us most of everything we need to know, because now finally we can get an answer here that says r as a vector is equal to 867 newtons, and it acts at an angle from the positive x-axis, which is 45 degrees plus the 63, or 108.0 degrees. Now, a word about significant digits. We are not going to apply the scientific approach to this. We're going to apply the engineer's approach. In the engineer's approach, or model for significant digits, is if it starts with a 1, use 4. Else use 3 significant digits. So A67 doesn't start with a 1, so it starts with an 8, so that'd be 867, right? We round the A66.91 up to 867, put the little decimal to indicate it's not exactly 867. And then here for the angle 108.0, even though there's a 0, I go ahead and include 4 digits. It's as simple as that. It doesn't matter what I start with, doesn't matter whether I'm doing subtraction or